When we consider the life story of stars, we generally think of stars ending up as black holes or neutron stars. While many stars do end up as those cosmological horrors, the vast majority are simply not massive enough for that. This includes over 97% of the stars in our galaxy, including our sun. So what happens to those stars? They eventually become cosmic entities known as white dwarfs. White dwarfs are the dense, faint stellar remains of smaller stars, and they do get their name from their size and color. Let's go through the process of how a white dwarf comes to be. Most stars are stabilized and emit radiation via nuclear fusion, specifically fusing hydrogen into helium. Our sun and other small stars do this via the double P chain. When they use up all their hydrogen, they turn into what are known as red giants and begin fusing helium into heavier elements like carbon and oxygen, triple alpha process. However, for stars smaller than 8 stellar masses, once they run out of helium fuel, they cannot undergo nuclear fusion. At this point, the star is considered dead. It has no elemental fuel to burn, so it cannot stabilize itself against gravitational collapse using the pressure generated by heat from the nuclear fusion. Instead, a different physical phenomenon stabilizes the dead star: electron degeneracy pressure. To understand how electron degeneracy pressure stabilizes white stars, we need to understand how urinals and the Pauli exclusion principle work. For every urinal, there can only be one person, and attempting to squeeze multiple people into a single urinal will result in people getting pushed out. In quantum physics, the urinals are quantum states, which are defined by quantum numbers such as the position, momentum, and energy, and the people are particles like electrons. The Pauli exclusion principle says that no more than one electron can occupy a given quantum state. If the states of two electrons are identical, they are called degenerate. With a white dwarf, the gravitational force is trying to squeeze electrons into the same quantum state and create degenerate states, but the Pauli exclusion principle prevents that from happening and repels electrons outward. This happens frequently enough to supply a constant counteractive force, which is called electron degeneracy pressure. Because the gravitational force is directly proportional to the mass of the white dwarf, there is an upper limit on how massive it can be before electron degeneracy pressure fails to stabilize it, generally accepted to be 1.44 solar masses. This is referred to as the Chandrasekhar limit. While a white dwarf is in this stage, it gets extremely hot and dense. 1 teaspoon of the stuff would weigh 5 tons. It is also extremely hot when it forms, reaching 180,000 Fahrenheit in its core and emitting a faint white light, which is where it gets its name from. Because there's no nuclear fusion to generate more heat, it gradually cools off and becomes inert, also known as a black dwarf. We haven't found a black dwarf yet, but because it's estimated that they take tens of billions of years to form, our universe is just over 10 billion years old, it may take a while. Alternatively, a white dwarf may be part of a binary star system and take in the other stars' matter. If it takes enough matter to surpass the Chandrasekhar limit, 10 to the negative 8 solar masses of hydrogen, it will undergo fusion again and detonate into a supernova.
Hi, so I will be continuing what Nick said and going more into the history of white dwarf stars. White dwarf stars were first originally discovered in 1844 when the German astronomer Friedrich Bessel noticed that the star Sirius had a dark object orbiting it, and it was moving slightly back and forth as if it too was orbiting another object, later discovered to be Sirius B. In 1863, Alvin Clark, the telescope maker, spotted what the object was using the telescope with an 18.5-inch aperture. He came from a family of telescope makers in Massachusetts that them too were also studying the Sirius star. And with this discovery, the Sirius binary star system was renamed with the stars being Sirius A and Sirius B, with A representing the bright star and B representing the dwarf star. It was so faint when Alvin Clark observed it that it was almost lost in the glare from Sirius A while not being any further away. Walter Adams with the Wilson Observatory looked more in depth at the star next to Sirius A in 1915 Specifically, they looked at the heat spectrum of the Sirius B star to figure out the mass of the star. What they discovered was that Sirius B is a star the size of Earth with a mass the size of the sun. It is about 3 million times more dense than water. This was determined to be a new type of star, i.e. the white dwarf star. In 1930, an Indian graduate student, Chandrasekhar, who was working at Cambridge at the time, applied their quantum ideas to stellar physics to come up with the theory of the origin of star formation that Nick mentioned. Finally, white dwarf stars are incredibly hard to detect due to their low luminosity. The easiest way to detect them is by looking for a binary star system that includes a white dwarf star. If there's a binary star system with a smaller unknown shadow orbiting it, it's likely that a white dwarf will be discovered from it. So some future enhancements that is done in the field of research surrounding white dwarf stars. The first one is X-ray signals, specifically from white dwarf star destruction. And as the universe gets older, white dwarfs also get older, and these X-ray signals also make it so it's easier to detect rather than just look for the luminosity of the star. Secondly, as Nick and Egan will have touched on briefly, white dwarfs are essential to the history of the universe since they give insight into the past and future of the universe by being so old. Thirdly, binary dwarf stars are a topic of discussion because the most often type of white dwarf star we see is in conjunction with another star. It is something that is being looked into and will continue to be looked into. And finally, further detection of white dwarf stars is very important by looking for white dwarfs in further galaxies, especially because they are so hard to detect with their low luminosity and X-ray signals that they give off, that looking for white dwarfs in further galaxies will help prove that they are one of the most common stars in the universe. Thank you.
Although white dwarfs are extremely difficult to detect due to their low luminosity, we still try to view them since all stars, including our sun, will become white dwarfs eventually. For context, using the Hubble Space Telescope, the brightest of white dwarfs appear as bright as if you were to take a single 100-watt light bulb and put it at a distance from the Earth equivalent to the moon. Nowadays, optical telescopes view white dwarfs best, but they can also be viewed by X-ray satellites such as Rosat or Röntgen satellite, a German one. While viewing X-rays from white dwarfs, we typically view their cores. Let's take a minute to recap the makeup of a white dwarf. The core is composed of carbon and oxygen, while the atmosphere is a layer of helium that surrounds the core, which in turn is surrounded by a layer of hydrogen. The atmosphere contains just helium and hydrogen, which are essentially transparent to X-rays that are emitted by the much hotter inner layers. There are typically two instances in which we are able to observe X-rays from white dwarfs during their lifetime. In a very young white dwarf, the core is extremely dense and can be as hot as 100,000 degrees Fahrenheit. These hot cores produce X-rays which we can use to learn more about dying stars. The other possibility is when a white dwarf is gaining matter from a partner star in a binary system, which accelerates this incoming matter to a point where it heats the surface of the white dwarf to a temperature of several million degrees, making the white dwarf appear very bright. When analyzing these X-rays, we can learn the mass of the white dwarf, its rotational speed, as well as the rate of matter joining the atmosphere of the white dwarf from its partner star. Now the question is, why do we care about this information and about white dwarfs in general? To answer this, the main importance of white dwarfs is that they can function as cosmochronometers, essentially timekeepers and chronological landmarks for the universe. We can use these dying stars to learn more about previous events in our universe, which in turn could help us anticipate any future events. This cosmochronometry is done by creating computer models for specific stars and inputting givens taken from X-ray analysis, such as the mass of the white dwarf, the rotational speed, and the rate of new matter. Challenges to these models include the unknown proportions of oxygen and carbon at the cores of white dwarfs. But the concept of cosmochronometry provides us with an opportunity to have a greater understanding of our universe in the past, the present, and most importantly, the future.